Okay, it's 2 p.m. Hello, everyone, and welcome to another Kent Seminar. Today we have Professor Alexander Brand from Virginia Tech. Professor Brand is an assistant professor at Virginia Tech, and he's also an affiliate faculty in the Material Science and Engineering department. And Professor Brand actually earned his bachelor's, master's, and doctorate degrees from UIUC. He just told me that he used to work with Professor Raisler in the building next door. So he's very familiar with UIUC and all the research we do here. His research interests include micro and nano characterization of concrete and physicochemical interactions between aggregates and cement paste. Today, he's going to be talking to us about physicochemical interactions between cement and asphalt because he knows the audience. And actually yesterday he had a presentation, another seminar in the materials seminar about a more materials related topic. And I'm really impressed by arranging or like preparing two presentations at the same time. So thank you, and please help me welcome.
Thank you, everyone. It's really great to be back. It's very nostalgic, right? I mean, I was back on campus in 2019 for a conference. Before that wasn't until 2015 when I graduated, right? So a lot of changes on campus, but it's good to see that some things just haven't changed at all, right? There's still really big cracks in the parking lot. We're an asphalt research lab, right? There's still a dilapidated building across the street. So anyways, it's very exciting to be back. So I really wish to thank you for the invitation to come back to give this talk. So today I'll be talking a little more chemistry than maybe people want to hear about. So if chemistry scares you, you can just like cover your ears or something and don't listen to those parts of the talk. But yeah, it's not going to be traditional civil engineering talk. It's going to be a little bit more on chemistry and material science. I did my PhD, I did my master's and my PhD with Professor Raisler, right? So, I did do some rigid pavement work, but really, towards the end of my PhD, I started doing more materials work. And then after my PhD here, I did a postdoc at NIST, and that was all on, nanoscale characterization of cements, right? So, I've really shifted more towards materials than pavements at all. So anyways, that's why it's going to be more of a materials talk. And then yesterday was, a nanoscale material science talk. So, hopefully today will be better because it is going to be a lot more on asphalt. So who in the audience works on asphalt? Right? Who's in cements? No one? One person? Okay. Okay. There's more people online. So yeah, hopefully the asphalt stuff will be exciting. But let's get this to advance here. There we go. All right. So just some nostalgic memories, right? So my first THE conference was 2009. I won one of the scholarship, when it was the Illinois County Engineers or something scholarship, right? So from Dr. Butler, he presented it, right? It was always great going to conferences with so many people. I couldn't find any TRB photos, but I was only able to find American Concrete Institute, right? Doing a lot of work. We did a really big project at the beginning of my PhD doing slab testing. So we're doing slab testing in the building next door, right? I'm really strong. I was able to lift those 1,000-pound slabs of concrete, right, to test them. But anyways, it was a huge project. Dr. Alcati even helped us cast the slabs. Dr. Raisler even helped us cast the slabs, right? We had a big project. I think we had 16 slabs or something to cast in one day, 4 concrete trucks. It was a lot of fun. It was also fun going out in the fields, right? Running out in the middle of traffic with some NDT equipment. You can kind of see some trucks in the background there barreling down the road towards me. Fun times, right? And probably some of the best memories, right? We're just with a great lab group. So I'm sure there's still some people here that only recently graduated, right? This photo's from 2015, and just to tell you how long it took some people to graduate there. Right? And then of course, probably my favorite memory is I was Santa Claus at the Christmas parties, right? So who's Santa Claus now? Do we still have a Santa Claus? Yeah. Oh, okay. So at least someone took up the mantle of Santa Claus. So anyways, it's still really great. Illinois has such a large network. All right, Dr. Race's group, you know, we see each other a lot at conferences. Right, he was a conference in Texas where he was right, you know, sitting on the Longhorn here, right? You know, so my group now at VT is not that large, you know, but I can aspire that one day, right, I'll be at a conference sitting on a Longhorn, right, and my group will be around me, right? That's what I hope to aspire to. But anyways, let's get into the talk. So again, you know, talking about the interaction between cement and asphalt. All right, so part of this is going to be an extension from my PhD work. So I'm going to introduce some of the stuff I did during my PhD, and then all the new stuff I'm doing at VT on a related, you know, sort of topic. So kind of an alternate title here is like, why can't we be friends? Right? You know, we do have bonding issues between, you know, overlays and things. But here we're kind of really looking into the chemistry as to, you know, how hydrating cement, you know, and asphalt basically chemically interact, right? How do they actually bond? Why do they bond? Things like that. So that's kind of what we'll be talking about today. All right. So of course, this work, you know, doesn't exist without the great people, you know, the great students I've had and the great collaborators we have. So I definitely want to give some great acknowledgement to the students and other collaborators on this project. So what's our objective here, right? So first off, so I'm going to come at this first from recycled aggregates, right? Because that was my PhD. My PhD was on using reclaimed asphalt pavement in Portland cement concrete, right? And I know everyone's going to suddenly like gasp, right? Like RAP in concrete? No, it only goes in asphalt pavement, right? But the answer is we simply just have too much RAP, right? And especially in urban areas where there's not enough area to stockpile it, we have to do something with it, right? So a number of states in the U.S. have looked at using RAP in concrete. There's been a lot of research out of India. They're starting to implement it a little bit more, right? So this is becoming a little bit more of interest. Some of this, so again, I'll be talking about RAP today. We're also doing some work on scrap tire rubber and kind of seeing some of the similar behavior we're seeing with RAP, right? So I'm going to call this just waste organic based aggregates, right? So petroleum based, you know, byproducts, right? So that's going to be tire rubber and RAP are really the ones we're talking about. RAS would probably also fit into that. We haven't looked at RAS, but that will also be in there. So anyways, we know there's some sort of bonding mechanism, you know, issue between RAP and cement paste. So that's what I found in my PhD. That's what I'll be showing a little bit here. The question is why? Okay, because if we can answer why and we can establish a mechanism as to why that happens, well, then we can devise a method to interrupt that mechanism, right? And then potentially improve bonding or somehow improve performance otherwise. Okay, so you know this is work from years ago that I did. Right, so this is, you know, increasing RAP content. We did fractionated RAP, so we also called it FRAP. So you'll see FRAP and RAP on here as well. Basically, just replacing up to 50% of the coarse aggregate in a concrete with RAP. You can see the significant reductions, right? We're dropping, you know, almost 50% down on tensile strength. It's a fairly significant drop. Right. So then traditionally we would have to over design our pavement to accommodate for that. But that was a different study. That's a different story. You actually don't have to, but I'm not going to talk about that today. So first off, you know, the first thought people had was, okay, well, your modulus is decreasing when you use RAP. Well, of course it is, right? You know, asphalt binder itself has a much lower modulus than concrete, right? No surprise there. But we actually proved that wasn't the issue. All right. So we went and we froze the concrete, right? So the point at which asphalt is going to become kind of stiff enough to be close to concrete. And we basically found that the modulus didn't change. Okay. Also, when you're using 50% RAP as a replacement of your coarse aggregate in the concrete, only 0.4% of the total volume of the concrete is asphalt. So is 0.4% asphalt really going to be the only reason why you're losing modulus, dropping modulus by 40%? That doesn't seem logical, right? So what we did then is we looked at something known as the interfacial transition zone. Okay, so this is the ITZ that this forms in concrete due to something called the wall effect. Okay, so in a concrete, all right, your aggregates, so the aggregate basically looks like a wall, right, relative to your cement grains, right? So cement itself also has a gradation, right? It's a very, very fine gradation, right? Mean particle size of about 15 microns, right? So 15 micron cement particle, you know, relative to a 25 millimeter coarse aggregate, yeah, that coarse aggregate is a gigantic wall, right? So it basically means there's going to be inefficient packing immediately against that aggregate wall, okay? So because of this inefficient packing, we form this thing known as the ITZ. Okay. So how do we study this ITZ? And we're going to talk about what the properties of the ITZ are in just a minute. Okay. Well, why didn't that? There it goes. Okay. So in order to study the ITZ, we have to look at a fairly small scale. Okay. The ITZ itself is only going to be about 20 microns to maybe 100 microns. Okay. Surrounding the aggregate, right? So that's pretty small. So we use an electron microscope. Okay. So an electron microscope, similar idea to a typical optical microscope, except we're using electrons instead of light, right, to image your surface, right? And instead of your eyes looking at the image, you have an electron detector that's reading the image, right? Sample preparation is really difficult. You have to take your concrete, you have to dry it out, you have to backfill all the pores with epoxy to stabilize the microstructure. Then you have to polish it really flat, and then you can put it in the electron microscope. All right, so that process alone took me 6 months of my PhD, right? But once it worked, right, we, able to get a lot of data. So anyways, so that's what we did, all right? And so what we would see then, so now this is a polished flat surface of concrete, okay? So here is our aggregate, okay? And here we're using something known as backscatter electron imaging. It's just one of the imaging techniques we can use with an electron microscope, okay? Everything shows up in grayscale. All right, so we can see our big aggregate surface here. Okay, everything that shows up as white is unhydrated cement. Calcium hydroxide is sort of this light gray. Everything black is porosity. They're filled with epoxy. And then now all the other grayscale is CSH and some of the other hydration products. Does this actually grayscale show up that well? I guess you can kind of see the color difference. It's a little bit difficult. But we use a computer to then do image analysis. All right. So here's an image of the wrap ITZ. Okay, so here you can definitely see asphalt mastic, right? So you can see there's some aggregates in this binder. And you can clearly see, that's why this image is very nice. And again, the grayscale is a little bit difficult to see here. But you can clearly see here, right? You have this zone that is definitely more porous, right? Right near that wrap particle surface relative to what would be the bulk. Okay, so you can definitely see a lot more porosity here. All right, so what we have to do here is just use image analysis. So I won't go through all the image analysis, but you basically threshold out what's the anhydrated cement, what's the calcium hydroxide, what's the porosity, convert it to a binary image, do some more image processing, and you can then basically get a gradient of these properties as a function of distance from the aggregate surface. Okay, and so when we do this over many images, okay, we can now come up with an average representation of what the ITZ looks like. All right, and what we definitely see for wrap, I thought I had it highlighted. Okay, so we have wrap up here, we have porosity, right? This is distance away from the aggregate surface, right? So the aggregate surface is at 0. Okay, so here's dolomite, that's our virgin aggregates, right? So that's just calcium magnesium carbonate. Right, we look at 3 different wraps, okay, and we can clearly see there's a lot more porosity for our 3 wrap samples relative to our control. Okay, so we have a larger, more porous ITZ surrounding all of our wrap particles. Okay, so that basically means we have a lot more porosity in our concrete, right? Pores don't carry weight, right? So that's why we're reducing our modulus, really. Right, it's because we now have a lot more porosity. Okay, and then there's some other uses. There was some interesting stuff with calcium hydroxide, unhydrated cement. Not a whole lot of changes. Okay, but really it's this porosity that's very different. Okay, now typically, when we're designing Portland cement concrete, we add a whole bunch of stuff to it. One of the things we typically use to make high performance concrete is to add something known as silica fuel. All right, that's a supplementary cementitious material, and we tend to get a much higher strength concrete, much more durable concrete. But what we found and what other studies have found is that adding silica fume to concrete with wrap did not make an improvement. So you were basically wasting money by using silica fume here. Silica fume is about 10 times more expensive than cement, so you're literally throwing money away, right? We still see there's a little bit of an improvement in porosity here, okay? But it's still a fairly large porous ITC. Okay, so silica fume doesn't fix our problem. Okay, so then we came to the question, all right, why do we have a larger, more porous IGZ? Why is it forming? Right? It doesn't seem logical that it would form. There has to be some sort of mechanism that's causing it to form. Okay. So everything up until now was stuff I did during my PhD. Everything from here on is kind of some of our new stuff that we'll be publishing soon. So what we know from the existing literature is that there are compounds in the asphalt that can leach. They can leach out of the asphalt. Okay. It does depend on what your solution is, right? Are we talking about rainwater? Are we talking about an acidic, I don't know, some sort of industrial water, right? We do know that there are compounds that will leach, right? So probably everyone here already knows asphalt is a very complex chemistry, right? There's no one molecule of asphalt, right? There's a very large range of molecular weights and chemistries and functional groups and heteroatoms and all that sort of stuff, okay? But anyways, so we do know that there can be leachate from asphalt. So our hypothesis then was, all right, well, when cement hydrates, it produces a very high pH pore solution, okay? So in a saturated concrete, those pores are not filled with air, they're filled with pore solution. That's a high pH pore solution, okay? So our hypothesis was, all right, that high pH pore solution is leaching compounds from the wrap, from the asphalt on the wrap, and that is somehow poisoning hydration. It's somehow preventing hydration from happening. And so that was our idea of what's going on here. All right. So then we set off to basically see if, that hypothesis made sense. All right. So the first thing we did was just a simple proof of concept. We took some wrap and we soaked it. Right. So we soaked some of it in an NaOH solution, sodium hydroxide. So again, pore solution is a high pH. It has sodium, it has potassium, it has hydroxyl ions and some other stuff, right? For simplicity, we just used NaOH, right, as an analog. Okay, much easier to work with. So we did a pH 12 NaOH solution. So we soaked the wrap in that, then we also soaked it in water. All right. And after a couple of days, every few days, we would take a sample out and send it to a TOC analyzer, total organic carbon. Okay. So in this technique, you basically inject your aqueous solution, goes through some sort of flame ionizer, and it tells you how much organic carbon is there. Okay, so it doesn't detect, for instance, CO2, right, dissolved in the water. That's not organic carbon. All right, so the organic carbon would be things in organic molecules, for instance, right? Asphalt is made out of organic molecules, right? So what we found, right, is that in the sodium hydroxide solution, we are definitely leaching a lot more organic compounds than we are in water. So, hey, okay, that's our first suggestion that maybe this hypothesis starts to make sense. Okay. So then we did something known as HPLC. Okay, so this is now we're getting into a lot more chemistry here. So this is high performance liquid chromatography. So here you take your sample and you drop it through a column that's going to be filled of something. Right? There's various types of columns. And you basically measure how long it takes for the various compounds in your solution to travel through that column. Okay, so depending on the polarity of the molecule, the size of the molecule, its adsorption characteristics and things, you're basically going to see different retention times. So how long it takes for that compound to travel through the column. You're going to see different retention times for different compounds. So what we're seeing here is a lot of peaks, which tells us there's a lot of different compounds. And that's maybe no surprise, right? Asphalt, again, is made out of a whole lot of different compounds, right? There's no one molecule we can define. So this kind of confuses everything because that's a lot of stuff here, all right? So then what we did is we basically took solution at specific retention times, right? So you have this liquid traveling through the column, okay? And then you grab that solution coming out of the column at specific times. Maybe I should use this so the audience online can see, right? You grab it at specific times, and then you can basically do chemical analysis on that. So it's a way for you to sort of segment out these different peaks, okay? So the first one is we took this main peak here, and we sent it through something known as a mass spectrometer. So in a mass spectrometer, you send your aqueous solution, it goes through a flame ionizer, or in this case, it was an electrospray ionizer or something. It basically ionizes your molecules, right? And then the mass spectrometer sends it along a magnet, right? And however long it takes to travel along that magnet tells you what the mass to charge ratio is. That's kind of a weird way to think about things. Okay, so it's the molecular mass of that compound divided by the charge, right? So, you know, it could be a 0 charge, 1 charge, 2 charge, 3 charge, whatever it is. Okay, so it kind of relates to molecular weight of the compound, but it's not necessarily the molecular weight of the compound. Okay, because that flame ionizing technique can basically fragment your compounds if it's a big molecule. Anyway, so it's probably more chemistry than people want to hear. So if this is where you want to put your hands over your ears, you can. Okay. Anyways, in summary, what we're getting at here, right, is really that main peak here. Okay, really only correspond, right? We had a couple of peaks in here, so there was kind of a bunch of compounds, right, in this specific retention time, but only one really big one. Okay, so this tells us that, okay, for the most part, this retention time was kind of just, you know, mostly one compound. What that compound is, we don't know, because that gets into a lot more characterization that we didn't have enough solution to do characterization, right? We literally were working with, you know, microliters of solution, microliters, not milliliters, microliters, right? And we need milliliters of solution if we were actually going to go and then do additional characterization. So that's maybe future work. So anyways, we then looked at different peaks here. Okay, so again, here now we're looking at the smaller peak. Again, a lot of peaks here, but really only one big one. So again, maybe for the most part, you know, that peak only had one compound, all right, or you know, one compound and maybe a few small other ones. But then it got a lot messier, all right, if we started looking at other peaks here, right? So here we're looking at this retention time here, and now we see a lot more peaks, okay? So again, all this is really telling us, right, is that whatever organic compounds are in this leachate, it's a whole bunch of different compounds, right? There's no one compound that leached out. Again, maybe not a surprise. Asphalt itself is not one compound, right? There's a lot of stuff there. So some other stuff we did then is we used Fourier transform infrared spectroscopy. Again, maybe a little more chemistry than you wanted to know. In FTIR, peaks correspond to specific functional groups. Okay, so basically when we compare, so this was just so this is kind of our blank scan, right, without any leachate, right? And here's the leachate from RAP. And for the most part, you see things are pretty similar, but you see a lot more peaks here, right? And basically these all correspond to sort of organic compounds, right? So again, that maybe not a surprise. But again, there's just no one compound in this leachate, right, that we can point to. And this is, again, what that sort of suggests. Okay, so now we know that there is something in the leachate, right? We do have organic compounds in the leachate. Are they actually affecting cement hydration? That is our next question. Okay, so here we use something known as isothermal calorimetry. We use this a lot in cement and concrete science. So as cement hydrates, it gives off heat. In a calorimeter, we measure how much heat is given off over time, right? And that gives us kind of an idea about the kinetics, okay? So what we're seeing here is we're looking at a control sample where we just mixed cement powder with water, right? And then the orange line is we mixed cement powder with that NaOH solution that had that organic leachate, right? And what we're seeing here is we're seeing a shift right, all right? So this main peak, this is our main hydration peak of cement. Okay, so we're seeing this peak shift to the right, which basically means that we did delay the rate at which cement hydrated. Okay, so there was some retardation, there was some change to how the cement was hydrated, right? We did delay it slightly. Okay, so now we kind of have an idea that, yeah, maybe this hypothesis does make sense. Next thing we did is we basically used a very large die press, and we squeezed out all of the pore solution from the concrete. Okay, you just put it under in a die, squeeze it all out. So we squeezed that out. So that's our pore solution that we pulled out from the concrete and send it to the talk analyzer. Okay, so red bars are mortars with RAP, right? Green is mortar with sand. All right, so you'll see that even the mortar with sand still had organic compounds. And that's probably because we have to use a fluoropolymer release compound in the die. Otherwise, it would never come back apart when we try to get our sample out. Okay, so picture like a Teflon spray, right? So of course, we're going to see, some organic compounds in our control. But regardless, right, we still see that if this is our control, because of the fluoropolymer and the dye, right, we still see a larger peak here, right, for mortar with red. So we definitely know that we are getting leachate in our concrete, right? So first we proved it just with, soaking in an NaOH solution. Here, this is actually in pore solution. And yes, we definitely have organic compounds. So let's reevaluate here, right? So we're thinking that the high pH pore solution of the concrete is leaching those organic compounds, and those organic compounds are somehow affecting cement hydration. Okay, so we haven't quite proven this last part, right? We thought it's just stealing calcium from solution. We don't know if that's true yet. That's future work. But at least what we've shown so far is, yes, we definitely have organic compounds in the leachate, in the pore solution, right? And we definitely are seeing some effect to cement hydration. Okay, so now we have an idea of what this mechanism is, why we might be getting this larger, more porous ITZ. So our next question is, hey, can we pre-soak the wrap, leach those compounds, right, and call it a day, right? Maybe we'll get better performance. So that's what we tried next. So we took all of our wrap, we soaked it in a high pH solution, again, sodium hydroxide, washed it, and then mixed it into our concrete or mortar. And it didn't work. So unfortunately, that hypothesis did not prove right, because what we actually saw is when we had wrap that was pre-soaked, we actually got a lot more organic compounds than the wrap that we never treated in the first place. So yeah, unfortunately, it didn't work. But some interesting stuff's going on here now. Okay, if we then test the strength of that mortar, okay, we actually did see, right? You can see there's a very slight difference here, right? So this is the pre-soaked wrap, this is the unsoaked wrap. Slight increase in strength, right? So these means are statistically different, 95% confidence. These other ones are not. Okay. All right. So we're seeing a very marginal increase in strength, right? Of course, we're not meeting, the equivalent of sand, right? The equivalent of our virgin aggregate, but we're seeing a slight increase. So was it really worth the effort? Probably not. All right. So next thing we tried to figure out, all right, so why isn't this NaOH working? And why are we seeing even more leachate after we're, sort of trying to pre-leach those organic compounds? All right, so the next thing we tried to do was some surface energy measurements. Probably some of you are familiar with this in this lab. When I was a PhD student, I used Dr. Alcade's equipment and did some of these measurements myself, right? So we're also doing these measurements still, all right? And so what we found, okay, is definitely after soaking the wrap in that NaOH solution, we are definitely somehow changing that surface chemistry. Okay, the surface free energy is changing, right? So this is just plain asphalt. This is asphalt we soaked in water just as like a secondary control, right? And this is asphalt soaked in that NaOH solution. Okay, so definitely we're somehow modifying that surface chemistry. Okay, and what you'll see here is when we actually compare this to the surface free energy of cement paste, we actually are seeing sort of a slight increase in the work of adhesion. Right? It's almost, kind of like a chemical bonding mechanism, a slight increase, right? Is it really solving our problem? Probably not really, right? But then we're still trying to figure out why is this NaOH affecting things? Okay, so next we did is we used something known as X-ray photoelectron spectroscopy, XPS. This is a purely surface science technique, right? This is measuring the surface chemistry only within the top few nanometers of a surface, okay? And so what we find is that we are definitely doing some sort of difference in chemical modification of the surface. We just look at the atomic ratios here, for instance, okay? We're doing some sort of slight modification to that surface when we're soaking it at NaOH, okay? Again, because remember, we are seeing more organic compounds after we treat it with NaOH, right? It's kind of doing the reverse opposite, right? The reverse effect that we were hoping for. Okay, and then just looking at, this is some more chemistry, just kind of do some peak deconvolution to figure out, some more about the functional groups that were present. But again, the only takeaway here, if you get, is just that we're somehow modifying the surface chemistry. Okay, What we're exactly doing, we don't really know yet. So anyways, in the end, right, did I solve the problem? No, not by any means. Okay. But at least we started to prove some more things here. Okay, so what do we know after all of this? Okay, so we definitely know that wrap aggregates do produce a larger, more porous ITZ. Okay, and that's one of the reasons for the reduced modulus and possibly reduced strength of our concrete when we use wrap aggregates. Okay. We do know that high pH pore solution in the concrete is leaching organic compounds from the wrap, right? We definitely know that. What those organic compounds are, we don't know yet. Okay. We definitely showed that, right? Again, these compounds, there's a bunch of compounds, right? We kind of saw that with a bunch of different techniques. We were not able to identify, right, what specific compounds were present, because there's probably just a lot of them. All right. Again, that doesn't make sense, or that doesn't, that shouldn't be a surprise when we know asphalt itself is fairly complex. Okay. And then we also showed that there appears to be a retardation of cement hydration. We're somehow delaying or negatively impacting cement hydration because of this leachate, right? We have not proved if it is some sort of mechanism that's stealing calcium like we initially thought. Right? That's something we still have to prove. All right. And then we also showed that sodium hydroxide solution to try and pre-leach the organic compounds did not appear to be very effective, right? A very marginal increase in strength. And then we saw much larger, organic compounds content in the leachate. So what don't we know? Okay, we don't know what that leachate is, right? We know it's a whole bunch of compounds, right? We know there's a whole bunch of functional groups. All those functional groups are just organic compounds. Doesn't really help us. Okay. The other thing we don't know is, are all of those compounds in the leachate affecting hydration, right? Maybe there's some compounds in that leachate that don't affect cement hydration whatsoever. Maybe there's some of them that accelerate cement hydration, are beneficial, right? In the end, we kind of saw that the net effect was negative, right? Net effect was a retardation of cement hydration. And the other thing we never really figured out is, what is the sodium hydroxide solution really doing, right? It's doing some sort of surface modification, right? We're seeing more organic compounds in the leachate, but then we also saw a slight increase in strength, right? So again, those don't quite really, align with what we were originally thinking here. So, of course, I presented this with respect to, wrap in concrete, okay? But that's not all that's relevant here, right? There's not many people looking at using wrap aggregates in concrete. I don't believe there's any state DOT currently even doing that, okay? Most find that the strength decreases, and they just say, well, it's not worth the effort, let's use some other aggregate, okay? So this is useful still, because we still see this effect with probably any organic, right? So we also are seeing this effect with scrap tire rubber, for instance, right? I didn't show those data because I only have so much time, right? We may also see this if we use grass or something, right? But this may also prove applicable to other things, okay? So here we're looking at concrete overlays of asphalt, right? BCOA, bonded concrete over asphalt. Not as common as asphalt overlays of concrete, right? But it's applicable here, right? So now if we're placing, fresh concrete on top of an existing asphalt surface, right? How is that bond interface forming, right? So we're getting some mechanical interlock, right? As cement paste sort of, seeps into the porosity and things at the surface, right? And maybe that's our best benefit, right? Because you're going to get an ITZ in that same scenario. We instead call it the OTZ, the overlay transition zone. Okay, again, it's only still tens of microns thick, but it's still there, right? So maybe we are getting this similar sort of behavior at that interface. This is also applicable if we're trying to figure out why and how organic compounds in soils negatively impact cement stabilization. Right. So currently, if you're trying to stabilize an organic soil with cement, what do? You just add more cement. Is that economical? No. Right. So can we interrupt that mechanism, right, to use less cement in that sort of situation? So that's another project we're hoping to kind of build off of some of this work. Maybe this also applies to when you're doing full depth reclamation and you're adding cement as a minor binder. Okay, is cement our best option there if we're seeing these negative impacts? I don't know, right? Maybe we're just adding too much cement. But again, if we interrupt this mechanism, maybe we can end up using less cement. So anyways, that's all I have. Thank you for your attention, and I'm happy to answer any questions. It looks like 35 minutes exactly. All right, yes.
Thanks, Alex. Great presentation and really interesting stuff. Just as an asphalt person, but one question for you: you focused most of your testing on the leachate and trying to understand what the composition of that was. Did you ever test the cement that was in the mix just to identify what hydration products were present, so that you could understand if hydration was actually being adversely affected, to verify your hypothesis?
Yes, so we do have all the characterization of the cement composition. We did not, so it's really difficult to quantify how much CSH is present from cement hydration, because it's an amorphous compound and we just don't have a good method of doing it. So no, we did not characterize that. So yes, I suppose the data then are indirect for proving that hypothesis.
I think it would give you a good sense if there's a way. Again, I'm not really a cements person, but if there's a way to do it, you could immediately get a sense, is what you think is happening where that calcium is getting stolen. That would probably give you an answer to that pretty quickly.
Yeah, I agree. That's an excellent comment. Thank you. Yeah.
Yes, very interesting presentation. I'm kind of the concrete guy.
Okay.
That's why I had to leave ICT, right? But I was just curious.
Behind you.
It was meant in jest. But I was curious. So in the pre-treated, where you soaked it in the NaOH, and you saw much higher organic compounds in that, but then when you tested it, you got statistically significant higher compressive strengths. That seems a little counter to the notion that it's those compounds. Is it possible that it could be related to the actual thickness of the asphalt binder layer over the aggregates, or?
So yes, we have, in a previous study we actually did with Errol and his imaging techniques, we did connect, the percent asphalt coating of the wrap to concrete fracture properties, for instance. Okay, so yeah, so that coating does affect your concrete performance, right? But if we're looking, so in this study it was all the same wrap. Okay. That pre-leaching in NaOH is not stripping away all the asphalt, right? I mean, we're probably not even affecting the thickness of that asphalt layer. We may be affecting sort of the surface roughness, right? We're probably affecting something about this. Well, we know we're affecting something about the surface chemistry, right? So my initial thinking of what's going on, right, is that yes, in that NaOH soaking, we are leaching some of the compounds that negatively affect cement hydration, but we're somehow still modifying the chemistry such that we're able to solubilize other compounds after the fact, but those compounds don't appear to affect cement hydration so much. And maybe that's what's going on. I don't know.
One little follow-up. Do
Yeah.
you happen to have any of the electron microscope imaging of that ITZ with the pre-soaked NaOH?
We did not, right? Because that's a whole other PhD in and of itself, just from sample preparation alone. That would be fantastic future work. We did do imaging of the wrap particle itself after that soaking. Texture-wise, not much difference, but color-wise, oddly enough, the color was very different after that soaking. So we don't really know. Clearly we're affecting something of that surface. What it is, to be determined. Stay tuned. Yeah. Earl.
Great presentation, Alex. Going back to the basics of some of the admixture stabilization reactions, like lime reactions or cement, the same calcium-based stabilizers. Anyway, there is always, especially with the organics, right? There is always this cation exchange capacity of organics so high, it prevents any kind of chemical reaction, therefore, with the cement reaction or calcium +2 reaction.
Yeah.
Is that a way to maybe look at this from an organic, is organic blocking things?
Yeah, so when you're saying cation exchange with the organic compounds, it's probably a different mechanism. Because when I think cation exchange, I'm thinking of clays, right? You're exchanging that interlayer,
Like
right?
cement, like-
Yeah, with organic compounds, what's probably happening is a cation complexation. Okay, so for instance, if the organic compound has a hydroxyl group or a carboxylic acid group, cations will complex with it. It doesn't bond, right? They sort of come together and they stay near each other. It forms a complex. Right? It's not quite a chemical bond. So that cation exchange you're mentioning is probably more of that type of mechanism where it is stealing those ions from solution, right? Because we need to reach a critical threshold of calcium in solution to start forming hydration products from cement, right? But if these organic compounds are stealing that calcium first, that's why I'm thinking we're seeing this delay, this retardation in cement.
Which is what's happening in stabilization.
And yeah, so we see that from stabilization too. And yeah, we started doing some of this calorimetry work for soil stabilization. We were surprised no one had done it before. So we've started to do that to kind of see the cement hydration delays in stable soils. So stay tuned for that work as well. Yeah, next.
Thanks for presentation. I have a question about the SEM results. So you did some quantitative analysis based on the SEM image.
Yep.
Compared to the whole test samples, SEM sample is really small. So how can you make sure that the small SEM sample could be good enough to represent the whole test sample? And if so, how do you select the SEM samples from the whole test?
So it's an excellent question. That's been a problem since people started doing this technique in the 80s, right? And it really comes down to a statistical representation, right? So when you prepare a sample, you take a random orientation from your sample. And then what I was showing with, if I go back to some of these ITZ results real quick. Stop sharing. I need to do that. I'll go back to sharing in a moment here. In case we lost that. Where is it? Here it is. Yeah. So these data here, I go back to sharing. People need to see. Right. So the data we're seeing here, right, as these IPZs, right, this is collected and averaged over many images. Okay, so multiple samples, multiple images per sample, all randomly oriented. Right. And so you assume that since you're randomizing it, you're collecting so much data, you're getting an average representation of the sample.
Have you ever compared the ITZ for samples before and after test?
After which test?
Maybe some comparative test or some test.
Yes and no, right? So it'd be difficult to do this type of characterization just because we'd see a lot of micro cracking, and therefore we would get sort of a skewed measurement of what the porosity is. So we'd have to somehow threshold out cracks. I don't know if anyone's actually even done that work. That's an interesting idea, actually. But yeah, I mean, you could do imaging of, let's say, a fracture surface. Okay. And one of the things we did find with this, so through the surface free energy measurements, we actually found that the energy of cohesion of the asphalt is less than the energy of adhesion with cement, which means that the crack will propagate through the asphalt film, not through the interface with the ITC. Okay, and that we were actually able to experimentally confirm. Okay, so that's one of the other reasons why we see a reduced strength in these behaviors.
Alexander, can you hear me?
Yes, I hear you.
Hey, Marshall. Hey, I typed a comment in soil organic matter that we typically encounter. I did my thesis in lime stabilization of soil.
Yeah, right.
And high organic soils will not react. I found that if you were to, we'd strip the organic out of a topsoil, treat it with lime, it reacted. And there is a shielding effect, a coating effect in that case. In other words, you can't get to the clay minerals because they're kind of coated and mucked up with soil organic matter. So I think you're on the right track. But the idea of exactly what the organic matter is in the leachate compared, say, to the organic matter in soils, you might look at some of that, but we
Yeah.
get the same Duke's mixture of, organic compounds in soil. And I think you're on the right track with the effect of, quote, organic carbon, unquote, whatever that might be.
Yeah.
But the idea of, in the case with soils, we just get rid of the organic content and the soils react.
Correct. Yeah. Yeah.
But that isn't working for you. Supposedly your leachates were, quote, reducing the organic content, but you're not really getting a lot of organic, the total organic in the wrap in the asphalt. I'm not sure you're getting a whole lot out by leaching.
Correct. And that's why we suspect it's only affecting the ITC. Right. So the wrap leachate, once we mix it into concrete, right, that leachate is only extending, right, 100 microns away from that interface, which is why we're forming that larger, more porous ITZ, but don't appear to be affecting the bulk microstructure. Right.
Yeah.
But yeah, in the case of soils, yeah, it is the same problem. The organics in the soils are very complex. There's a lot of different compounds. What we've been doing lately is basically developing our own, simulated soil, I guess, right? So using, we've done some tannic acid experiments in just a clay sample, for instance. And we're starting to do some measurements to see, is the cement hydration delayed? And yeah, we are seeing an effect.
Years ago, the folks in the United Kingdom developed a test for evaluating whether or not there was enough organic in a soil to significantly, screw up the hydration. And it's a 10% lime treatment, 10% cement, with the soil. And then you check the pH, and if the pH doesn't make it up to the 12.3 level,
Okay.
it's then you're suggesting that hey, we're screwing up hydration. You're getting the calcium hydroxide popping over from hydration of the cement. So I think you're on the right trail. I think you got a major task at hand in terms of trying to unravel the problem with the wrap.
Yes, so this is what we've discovered.
Yeah.
Right. Yeah. Yeah, thank you. Did we have any other comments?
Not in the chat. Do we have any
Okay.
questions in the room? Okay, if not, please stick around. We have a meet and greet session with Professor Brandt, and let's thank you for the nice presentation.